Right, we need to look at the magnetic field produced by a current carrying loop. So we're going to start out with this picture here that I've got of a loop where there's a current I going through this loop. And we want to figure out the magnetic field at some point P out here. So we want to figure out the magnetic field along the central axis. So the loop is centered on the y-axis here, and so we are trying to find the magnetic field, both the strength and the direction, at any point along the y-axis, right? So that's what we're gonna try to do. So in the picture, you can see that we've got this loop of current, and so we're gonna have to write out an expression for the contribution to the magnetic field due to the chunk of wire here, down here, right, all throughout the entire wire. And so we're going to have to leverage the Biot-Savart law. So if you look here, I've got Biot-Savart written down, and I want to point out that the book kind of makes it hard on us because in the Biot-Savart definition, the sine theta that's listed here, that refers to the angle between DL and R, which turns out is not the angle that's in this picture. That is not the theta that sine theta is referring to. And so once you realize that, you recognize, oh, well, the angle between DL and R, that's this angle right here, like the angle between this and R. So that's actually 90 degrees. So sine of 90 is 1, and so we just simplify the Biot-Savart expression as DL times 1. And then I've substituted out the r squared value for y squared plus big R squared, just using the Pythagorean theorem. All right, so that's the starting point for the Biot-Savart, and of course then we're going to have to add up all of the contributions going all the way around the loop. Now, this next expression that I've written down is where we're going. So we need to integrate dB, right, that small chunk of the magnetic field. We need to integrate that from all the contributions over the entire loop. And so if you look at the picture here, and I've drawn this arrow to kind of point you in the right direction, if you look at the picture, each spot, say up here on the wire, has a corresponding spot at the bottom of the wire where the magnetic field will be the same magnitude, but it'll be one of the vectors will be pointing up and one of the vectors will be pointing somewhat down, and the components of that vector in the z direction are going to cancel, right? One's pointing up, one's pointing down, those will cancel. But both of the vectors have components that are pointing in the y direction, and so those are going to add together. Those are going to survive when we integrate and add up all of the terms. So what that means is that when we take this dB, all that's going to survive is the component along the y-axis, which is why I've got this cosine term, because it's not dB that's going to we're going to add up. It's just the portion that's pointing in the y direction, and so that's why I also have the j hat vector there, because this vector is going to be pointing along the y-axis. Now, if you look up at the picture, the cosine of theta is equal to r, and then divided by r, little r, which is the square root of y squared plus r squared. So I'm going to plug that in for cosine, which is what I do in the next expression. So down here, I've written out dB, which is mu naught I over 4 pi dl over y squared plus big R squared. And now I'm multiplying by the cosine term, so that's multiplied by cosine of theta, and then including the direction there, right, because B is a vector. So now I'm going to jump to the next line, and you'll notice something interesting about this next line. Notice I have pulled all of the terms outside of the integral except for dl. Why did I get to do that? Well, because dl is the integral. We're integrating the path over the loop, right, as we go around the loop. Well, that doesn't depend on r, the radius of the loop. It also doesn't depend on, right, r is just a constant value. And y, the variable for how far along the y-axis we are, that's also not going to be related to going around the loop. And so all we're going to do is integrate over the loop, which is equal to the circumference of the loop, 2 pi r. So I get to just immediately substitute this expression right here, 2 pi r. I get to substitute that in for this, right? I'll immediately do that. So when I do that, I get this expression down here. This is the expression for the magnetic field produced by a current carrying loop along the central axis, right? So anywhere along the axis, this is the magnetic field. And again, for this particular problem, the way that the loop was oriented, the direction would be along the y-axis, right? It would be pointing in the positive j-hat direction. And typically, something that's very useful is to ask, what's the strength of the magnetic field at the center of the loop? And that's when y would equal 0. And so if you set y equal to 0, you end up getting that the magnetic field strength at the center of a loop is mu naught I over 2r. And over here, so let's just highlight that. And then over here, I've got a picture of the general mapping of the magnetic field due to a current carrying loop. So you've got the field always pointing, so this is where we solved for, along this sort of central axis. That field is always pointing from left to right in this setup. And you can see that even though they're not all drawn, all of the magnetic field lines are actually loops, right? So they're loops around, loops that close. They don't start or end anywhere, right? They're just continuous loops. And again, that's a feature of magnetic field lines that is different than our electric field lines. All right, so this was an example of using the Biot-Savart law to determine the magnetic field due to a current carrying loop. And so now that we've done that, we know any time that we have a problem where there's a current carrying loop and we want to find the magnetic field along the central axis, we can immediately go to these two expressions, these two. We can immediately use those to solve problems, right? We don't have to redo the calculation. We know what the two expressions are.